I would like to talk today about some developments of quantum mechanics. In my talk on Thursday, I gave the basic structure. The basic structure consists of some dynamical variables, which are non-commuting quantities, and you have to be given the commutation relations between them in order to make them definite. When you have these definite dynamical variables, you need a Hamiltonian, that is to say, a quantity which represents physically the total energy and which is a function of these dynamical variables. When you've got the Hamiltonian, you can proceed to set up the Heisenberg equations of motion. For any dynamical variable u, we shall have IH du by dt equals u times the Hamiltonian minus the Hamiltonian times u. That gives us the Heisenberg scheme of equations. Alternatively, there is the Schrödinger formalism, in which we work with a wave function psi, and the wave function satisfies this wave equation IH d psi by dt equals capital H psi. This capital H is the same Hamiltonian which is now interpreted as an operator operating on the wave function. Now, I want to apply this to a dynamical system containing many similar particles. The wave function in that case will involve the dynamical variables of each of these particles, and we shall have the possibility of the wave function being symmetrical between the particles. The Hamiltonian, H, has to be symmetrical between the particles. It represents the total energy, and there's nothing to distinguish one particle from another. H has to be symmetrical. If psi is symmetrical, then d psi by dt will be symmetrical, and that means that if psi is initially symmetrical, it always remains symmetrical. So that we have a situation that a wave function that is initially symmetrical always remains symmetrical, and it may appear as a law of nature that only symmetrical wave functions occur. For some kinds of particles, we do have this law of nature, and those particles are called bosons. They follow a different kind of statistics from classical statistics, the statistics that was first worked out by Bose. With this statistics, one sees that photons have to satisfy this statistics, because the statistics then leads to Planck's law for blackbody radiation, so that we can assert that photons, light quanta, are bosons. Now, we have psi, our wave function, a function of the dynamical variables of the different particles. Let's say Q1, the first particle, Q2, the second, and so on. This Q is a single letter which denotes all the variables needed for describing, all the commuting variables needed for describing a state of that particle. We specify a point in the domain of this wave function by specifying all these Q's. Now, another way of specifying the wave function would be to say how many q's have one particular value, how many q's have a second value, how many q's have a third value, and so on. Instead of saying the value of each individual q, we say how many q's have a certain value. This new way of specifying the state for the whole assembly, the big psi, is just as good when the wave function is symmetrical. If it were not symmetrical, that wouldn't do, because then you would have to distinguish which bosons are in which states. But when it is symmetrical, that distinction is no longer needed, and it is sufficient just to describe which states are occupied and how many bosons are in each of these occupied states. We get in that way a possibility of transforming psi to new variables, n1, n2, n3, and so on, n1 being the number of q's equal to q1. Well, I'd better perhaps call these A, B, C instead of 1, 2, 3, because there's no correlation between these suffixes and these suffixes. N1 is the number of q's having the first value, N2 the number of q's having the second value, and so on. We can then use these n's as dynamical variables. We have in that way a new description in terms of these new variables n. Each of these n's denotes the number of bosons in a certain state. Each of these n's is a dynamical variable which has for its eigenvalues 0, 1, 2, 3, 4, and so on. Just integral eigenvalues. And these n's commute with each other. If we specify the number in one state, that doesn't interfere with our specifying a number in another state. Now I want to study one of these variables n, whose eigenvalues consist of the numbers 0, 1, 2, 3, and so on. You will immediately see a connection between that n and the energy of a harmonic oscillator. A harmonic oscillator has a set of energy levels in arithmetical progression. We can choose our numerical coefficients so that the differences of these energies is equal to 1. There is a 0-point energy of a half a quantum for a harmonic oscillator. Let us subtract that out, and then we're left with an energy having the values 0, 1, 2, 3, corresponding exactly to the eigenvalues of one of these n's. That means that we can picture each of these n's in terms of a harmonic oscillator. A convenient way, the most convenient way of describing a harmonic oscillator is by means of the Fock representation. I will just say what are the basic ideas of this representation. We are dealing with a harmonic oscillator. This is now a different problem from what we were dealing with up there. While the energy H is equal to a half P squared plus Q squared minus the 0-point energy, where we are taking the simplification of H equals 1, N equals 1, omega equals 1. Cutting out all these unnecessary numerical coefficients. Now, the basic state for this oscillator has the wave function, which we may call psi naught, e to the minus a half q squared. This is the wave function representing the basic state of an oscillator. Let us introduce this variable eta equal to 1 over root 2 p plus iq. This is a complex variable, p and q being real. It has its conjugate, eta bar equals 1 over root 2 p minus iq. And if we work out eta bar, eta minus eta bar, using qp minus pq equals IH, the standard quantum condition, we find that eta bar, eta minus eta bar equals 1 over root 2, 1 over 2 well, I won't work out the details. It turns out to be just equal to 1. And that means that eta bar is equivalent to the operator of differentiating with respect to eta. The Fock representation consists in working with eta and eta bar. Let's take this psi naught and operate on it with eta bar. Eta bar psi naught, put a root 2 there, and we get p minus iq psi naught. P is equal to minus IH. Well, we're taking h equal to 1, so it's just minus I. Minus I q plus p minus I d by dq plus q psi naught equals naught. Eta bar applied to psi naught gives 0. Let us consider some function of eta and eta bar expressible as a power series. Now, using this computation relationship, in this function of eta and eta bar, we can shift all the eta bar factors to the right. And then if we have this function of eta and eta bar applied to psi naught, shift all the eta bars to the right, any eta bar applied to psi naught will then give 0. We shall be left with some function g of the etas only applied to psi naught. And the result is that the only independent functions, the only independent wave functions that are left are psi naught, eta psi naught, eta squared psi naught, eta cubed psi naught, and so on. The energy H equals eta bar eta eta bar. That H, which I had previously, this H here just goes to eta bar. And if you apply this H to eta to the power of r psi naught, you get r times eta to the r psi naught. And that means that eta to the r psi naught is that stationary state of the oscillator for which the energy is, the energy excluding 0 point energy is just R. If If you like, you can say that this is the unexcited state, this is the first excited state, this is the second excited state, eta to the rth sine naught, the rth excited state. And there we have all the different excited states of the oscillator represented in a very simple way. Now this representation of Fock is most useful in our present connection. What we do now is we introduce one oscillator for each boson state. Not one oscillator for each boson, that would be quite wrong. One oscillator for each boson state. Now there might be n bosons in that boson state, and then we make that correspond to the oscillator referring to this boson state being in its nth excited state. In that way, any state for the assembly of bosons can be connected with a state for the oscillators. The number of bosons in any boson state is equal to the degree of excitation of the corresponding oscillator. This is rather a remarkable fact, and it forms the basis of the reconciliation of the wave and corpuscular theories of light. If we look upon light from the corpuscular point of view, then we have the photons, which are bosons, and they have to be handled according to this general theory of bosons. If we look upon light from the wave point of view, the different Fourier components of the waves are harmonic oscillators, and they may be handled by this Fock treatment here. We see now the connection between those two treatments, and we see that an assembly of bosons and a set of oscillators are just two mathematical descriptions for the same physical reality, so that the electromagnetic field may be considered either as a set of photons or as a set of electromagnetic waves. Those are two mathematically equivalent descriptions for the same physical reality. That is the basis of the reconciliation of the wave and corpuscular theories of light. Now we have these variables eta and eta bar occurring in the Fock treatment. There's a simple physical meaning for these etas. The eta operator increases the degree of excitation by one quantum, while eta bar reduces the degree of excitation by one quantum. We understand now this equation here. Eta bar psi naught equals naught. If we take the unexcited state and try to reduce the degree of excitation by one quantum, we get zero. That is immediately evident physically. So that we have now a mathematical description of the electromagnetic field in terms of these operators of increasing or decreasing the degree of excitation by one, and that also can be described by saying they are the operators of emission and absorption of a boson. The etas are the emission operators, which increase the excitation by one. The eta bars are the absorption or destruction operators which reduce the excitation by one. We shall have one set of variables, eta A bar, one pair of variables for each boson state. What are the commutation relations between these variables? They consist of the following. Variables referring to different boson states will commute with each other. Eta A, eta B minus eta B, eta A equals naught. Eta A bar, eta B bar minus eta B bar, eta A bar equals naught. The emission operators all commute, the absorption operators all commute. Eta A bar, eta B minus eta B, eta A bar is equal to 0 when A and B are different, and is equal to 1 when A and B are the same. So we put here the Kronecker delta AB. When we are dealing with the electromagnetic field, or with any assembly of bosons, we need, for the description of a system in quantum mechanics, these variables eta and eta bar satisfying these commutation relations. Now, I've been talking about an assembly of bosons. One might start off with a wave function for similar particles, which is antisymmetrical between them instead of being symmetrical. Take this psi to be antisymmetrical. If psi is initially antisymmetrical, it remains always antisymmetrical. We have now a new possibility referring to a new kind of particle. Particles of this kind are called fermions. They are such that two of them cannot be in the same state. If that psi is antisymmetrical, then we mustn't take two of these q's equal, or we get 0. The fermions are those particles such that two of them cannot be in the same state. That property applies to electrons. That's Pauli's exclusion principle. And it applies to several other of the elementary particles in nature. We may proceed to develop a theory of fermions analogous to this theory of bosons, but the fermion variables will not be related in any way to harmonic oscillators. It's only the bosons that are related to harmonic oscillators. However, even in the case of the fermions, we can introduce the operators eta and eta bar, which refer to emission and absorption of a fermion, just like these refer to emission and absorption of a boson. I don't have time to go into the details of the development of this theory of fermions, but I will just say what the result is. We again have these eta and eta bar operators, and eta bar being associated with each fermion state, and the etas and eta bars now satisfy different commutation relations. Instead of these equations here, which apply to bosons, we have these equations which apply to fermions. Eta A, eta B, plus eta B, eta A equals naught. Eta A bar, eta B bar, plus eta B bar, eta A bar equals naught. Eta A bar, eta B, plus eta b, eta a bar equals delta a b. Just the same equations, except that we have plus signs here instead of minus signs. That is, seems to me, a very remarkable mathematical fact. I don't know what really lies behind it. There are two quite different physical situations. Here we're dealing with particles such that any number of them can go into one state. Here we're dealing with particles such that two of them cannot be in the same state. Very different physical situations, but there is such a close parallel between the algebraic equations in the two cases. Suppose we take this first equation and put b equal to a. If we put b equal to a there, then we get the equation eta a squared equals 0. Well, that means simply that we cannot have two fermions independent of the same state. If we try to do it, we get 0 for our wave function. This is an equation which doesn't have anything corresponding to it in the boson case. The number of particles in a state, Na equal to eta a bar, has the eigenvalues 0, 1, 2, 3, and so on in the boson case. In the fermion case, we have again Na equals eta a bar, and that has the eigenvalues 0 and 1 only. The number of fermions in any state is either 0, the state is unoccupied, or it is equal to 1, the state is occupied, and then it is completely full and no other fermion can jump into that state. Well, these are the basic dynamical variables which are used in any quantum theory of fields. There's a rather technical generalization which one has to make. I'm assuming here and here that the different states are all discrete, but that will not hold in practice. One will usually take the different states to be momentum states for our particle. The suffix a will then be replaced by the 3 momentum values for the particle, plus the spin value if the particle has spin. When we do that, the delta AB, which we have here and here, is to be replaced by delta P1 prime minus P1 double prime, delta P2 prime minus P2 double prime, delta P3 prime minus P3 double prime. This is just a technical generalization which we always have to make when we pass from discrete quantum states to a continuous range of quantum states, and it doesn't have any serious effect on the structure of the equations. Well, that answers the first part of our problem of deciding what dynamical variables we are to use in describing quantum theory for a field. The next question is to find the Hamiltonian. The Hamiltonian is the total energy. The Hamiltonian, in the case of the bosons, well, in any case, the Hamiltonian has to be chosen so as to give correctly the equations of motion. And I would like to illustrate how that is done by taking the case of the of a field of radiation by itself. Take the electromagnetic field and suppose there are no charges present, so that we just have a field of photons. We may use as our dynamical variables the electric and magnetic fields. We have to take the dynamical variables throughout the whole of space at one particular time. That is to say, the vector E at the point x1, x2, x3, that is to say, at any point in three-dimensional space, at a certain time. And this E will be a vector, so we must put in the suffix r, taking on the values 1, 2, 3, the three components of the vector. And similarly, we have H, x1, x2, x3. These are the dynamical variables which are needed to describe the electromagnetic field of pure radiation. You notice that we have rather departed from the four-dimensional symmetry which we like to have in a relativistic theory. That is inevitable when we go over to a Hamiltonian formalism. We are departing from the four-dimensional symmetry, and we cannot help it. These are the E and H at a certain time. The Hamiltonian is equal to the total energy, and we take this to be the same as in the classical theory. H equals 1 over 8 pi integral of E squared x1, x2, x3 plus H squared x1, x2, x3 integrated over the three x's, dx1, dx2, dx3. Now, what are the equations of motion for E and H? Well, we know what they are from the Maxwell theory. dE by dt equals curl H, dH by dt equals minus curl E. Have I got a minus in the right sign? In the right one? I can never remember that. I think I have this. And we also have equations div E, div H equals naught. For those equations, div E, div H equal to naught are constraints which are to be applied to these variables here. These are the equations which tell us how E and H vary with the time. They must correspond to the Heisenberg equations of motion in the quantum theory. So that in the quantum theory we should need curl H equals curl H multiplied by IH is equal to EH minus HE IH. Curl E equals HH minus HH. This holds for each of the three components of the vectors on each side. So we can write down these Heisenberg equations of motion, and now we can infer what the commutation relations are between these quantities E and H. We have to set up suitable commutation relations between these quantities E and H to make these equations follow when this Hamiltonian is taken to be this expression here. That is quite a definite problem which we can easily work out, get a definite answer to. The result is that we find that the different components of E throughout space all commute with each other. The different components of H, this H throughout all space, all commute with each other. One component of E and a perpendicular component of H don't commute. If the two field points are very close together, we have the derivative of a delta function coming in. In any case, the commutator of one of these and one of these is a number. We can take suitable linear combinations of these quantities so as to get commutation relations similar to these here. The result is that we get these commutation relations describing the variables for the electromagnetic field, and we find also what we are able to introduce also the variables eta bar, referring to emission and absorption of a photon. In that way, we get a satisfactory theory for the electromagnetic field as taken over into the quantum theory. We can do the same with an assembly of electrons. And then we can furthermore introduce the interaction between the electrons and the electromagnetic field. In each case, we have to put down the Hamiltonian, which is suggested by taking the well, I should say in the first place, for the electrons by themselves, we put down the Hamiltonian, which just represents the energy of the electrons, and then we choose the commutation relations to give the correct equations. Then we bring in the interaction by suitably equations. Then we bring in the interaction by suitably bringing in extra terms into the Hamiltonian, which lead to the correct Heisenberg equations of motion. The result of that is that for an assembly of electrons and the positrons which go with them, interacting with the electromagnetic field, we can obtain quite definitely the Hamiltonian, the total energy of that dynamical system. This Hamiltonian will consist of some terms which represent the energies of the particles by themselves, plus some terms which represent the interaction energy between the particles. The usual way of handling such a Hamiltonian is by a perturbation method, and one looks upon the interaction part of the Hamiltonian as giving rise to transitions in which some particles are emitted and some are absorbed. For each of these transitions, there is conservation of momentum, but there is not conservation of energy. Now you may wonder why there is this difference between energy and momentum. The difference arises because we're talking about the energy at one instant of time. This H applies to one instant of time and is integrated over the whole of three-dimensional space. And when we're talking about one instant of time, energies are not well defined. And interaction images then do not have to be conserved when a jump is made. There's just one development of this theory that I would like to point out, which is really very neat and satisfying. In the first place, one obtains this Hamiltonian in terms not merely of the electromagnetic variables which I had in this discussion, but of rather more general electromagnetic variables which include some longitudinal electromagnetic waves. This is a field of pure radiation with only transverse electromagnetic waves. So long as you're dealing only with transverse electromagnetic waves, you cannot bring in the Coulomb interactions between particles. To bring them in, one introduces in the first place some longitudinal electromagnetic waves, but there is a mathematical transformation that one can make which results in their elimination. You would like to eliminate them because they are rather remotely connected with the experiment. And the result of this elimination is to give you some new variables for the emission and absorption of electrons. These new variables have a simple physical meaning, namely, one can suppose that the new variable eta refers to the emission of an electron together with the Coulomb field around it, not just a bare electron. We get a new theory where the electron is always accompanied by a Coulomb field around it. Whenever we emit an electron, we always emit this Coulomb field, forming a sort of dressing for the electron. And similarly, when an electron is absorbed, the Coulomb field around the electron is simultaneously absorbed. This, of course, is very sensible physically, but it means a rather bigger departure from relativistic ideas, because if you have an electron which is usually moving like this, the Coulomb field around it at one instant is spherically symmetrical. And it is this spherically symmetrical Coulomb field which has to be emitted together with the electron. When we make this transformation, a transformation which results in eliminating the longitudinal electromagnetic waves, we get a new term appearing in the Hamiltonian, and this new term is just the Coulomb energy between all the particles. E1, E2 over the distance R12, summed over all the electrons which happen to be existing for the state that we are concerned with. This term appears automatically when we make this transformation of elimination of the longitudinal waves. Well, this part of quantum electrodynamics is really quite satisfactory. I've only been able to give you a brief outline of it because there isn't much time, but still one can fill in the details and make everything seem okay. However, when we go on to consider getting solutions of our equations, then we run into trouble. If we're going to get solutions, then in the first place, one thinks of the Schrödinger equation. IH d psi by dt equals H psi. And the natural way of getting these solutions is a perturbation method, where all the interaction terms are treated as causing a perturbation. If one tries to get a solution on those lines, one starts with some definite initial state. One gets the first order correction, that's all right. Then one gets the second order correction, and one is led to integrals which are infinite. Whatever initial state one chooses, one always gets these infinite integrals appearing in the course of the solution. Now that is really very unfortunate, and I think the proper answer to say, the proper conclusion to come to, is that this Schrödinger equation doesn't have any solution. At any rate, no one has found a solution, although people have studied it for decades, and I think the answer is that it just doesn't have solutions. You might say, suppose we take a very simple case. Suppose we start off with a psi for which there are no particles present at all. No electrons, no positrons, no photons. Then apply the perturbation method. Well, we find that starting off with no particles, we do get particles created. Our Hamiltonian contains terms which correspond to the simultaneous creation of an electron and a positron and a photon. These three things are all created together with conservation of momentum, but without conservation of energy. The result is that our state does not remain a state of no particles. Particles get created in the first approximation, and then one goes on to the second approximation, and one finds infinities. One cannot even get a solution starting with this very simple case. Now you might say that when there are no particles present, that's a vacuum. That cannot be the case. The vacuum must be a stationary state. The vacuum must be a state with a lot of particles present, and it must correspond to some stationary solution of this Schrödinger equation. But no one has been able to find the solution of the Schrödinger equation which represents the vacuum. It's true that there are no solutions known of the Schrödinger equation, not even the solution which represents the vacuum. Now you might say that's a very unfortunate situation, and that we cannot do anything at all with this theory. But the situation is not really as bad as that, because from the experimental point of view, we don't want to do calculations about the vacuum. There's nothing the experimenter can do which will give you any information to compare with a calculation about the vacuum. Experimenters are only concerned with departures from the vacuum. We may depart from the vacuum by taking the psi for the vacuum state and applying to it an operator of emission of a photon. I don't mean a photon, I mean an electron. That's the more interesting case. Let us apply the electron emission operator to the psi for the vacuum. We don't know what psi for the vacuum is, but we can apply the Heisenberg equations to this operator of the emission of the electron. And then that will tell us how this thing varies with the time. Well, the difficulty with the infinities is perhaps not quite so bad under these conditions, but even so, in the second approximation, when we try to solve the Heisenberg equations, we get an infinity coming in. This infinity can be interpreted as an extra self-energy for the electron, which happens to be infinitely great. That leads to the idea of renormalization. People say that the mass of the electron, which one puts into the equations at the beginning, is perhaps not the same as the observed mass. And that when we take into account the interaction of the electron with the electromagnetic field, that interaction might change the mass and give a different observed mass from the original mass parameter in the equation. That's quite a reasonable physical idea if the change in the mass is small, or even if it is not small, provided it is finite. But it's very hard to attach any sense to it when the change in mass is infinitely great. It is true, though, that the infinity which one gets from trying to solve this equation is just of the same nature as one would get with a renormalization of the mass. I might specify it a little more closely by saying that this infinity is of the form integral d nu, where nu is the frequency of the emitted photon when one takes into account the perturbation term in the Hamiltonian, resulting in creation of an electron-positron pair and a photon. This nu represents the frequency of the photon, and allowing all photons up to infinity gives, of course, an infinity here. And one can trace an analogy between this infinity and the infinite rest mass of an electron in the classical theory, the classical Lorentz theory for a point electron with a Coulomb field around it. The Coulomb field contributes an energy, and when one integrates this energy, taking the electron to be a charge concentrated at the point, one gets an infinity, which is of essentially the same nature as this one here. However, this situation is somewhat modified when one takes into account the complete electron theory, where we have positrons as well as electrons, the positrons appearing as holes in a sea of negative energy electrons. One gets a different kind of infinity when one takes this complete picture into account, and this integral gets replaced by the integral 1 over mu du, a logarithmic infinity, sort of a logarithmic log mu taken with mu going to infinity. It means that this complete theory of electrons does make the infinity less severe, and that can be understood physically in this way. In this complete theory, the presence of a charge here will produce a polarization in the vacuum around it, because it tends to produce electron pairs, which will to some extent compensate for the Coulomb field produced by this original electron. And it is this compensation which makes the infinity less severe. But still it is an infinity. Well, in spite of these difficulties, people have gone on to do extensive calculations on these lines. They have calculated how the energy of this electron connected with this emission operator is affected if there is an external electric field or an external magnetic field. And people have found that the external electric field or the external magnetic field produces a small correction in the energy. You have to subtract the infinite term in either case, and this small correction is then interpreted as giving the Lamb shift in the case of the energy levels of hydrogen, or the extra magnetic moment of the electron, the anomalous magnetic moment. These calculations do give results in agreement with observation. When most physicists are very satisfied with that situation, they say quantum electrodynamics is a good theory. You don't need to worry about it anymore. I must say that I'm very dissatisfied with the situation, because this good theory, so-called good theory, does involve neglecting infinities which appear in your equations, neglecting infinities in an arbitrary way. And that's just not sensible mathematics. Sensible mathematics involves neglecting a quantity when it turns out to be small, not neglecting it just because it's infinitely great and you don't want it. One can put the calculations of the Lamb shift and the anomalous magnetic moment into a sensible form by introducing a cutoff, by making these integrals not go to infinity but to some upper limit, and you show that the interaction between the electron and the electromagnetic field is cut off for frequencies beyond a certain limit. One can take this cut-off frequency to correspond to an energy, let us say somewhere around 1,000 million volts. Owing to this logarithmic, owing to the appearance of the logarithm here, that cutoff will not give appreciably different results, so that you still get effectively the same Lamb shift, the same anomalous magnetic moment when you work with these cutoffs. However, you have a theory where the infinities have gone. You have a theory which is sensible mathematically, but the unfortunate thing then is, of course, that the relativistic invariance of the theory is spoiled. If you have any cutoff at all, saying that nu must not exceed a certain value, that is a non-relativistic condition, and it spoils the relativistic invariance of the theory. One can make electrodynamics into a sensible mathematical theory at the expense of spoiling its relativistic invariance. But I think that that is preferable to departing from the standard rules of mathematics and neglecting infinite quantities. And I feel that I disagree with most of the physicists at the present time, and just on this point, I cannot tolerate departing from the standard rules of mathematics. Of course, the proper inference from this work is that the basic equations are not right. There must be some change introduced such that these infinities don't occur in the theory, so that we can carry through the solution of the equations sensibly according to the ordinary rules of mathematics without being bothered by these difficulties. That will mean some very drastic change. No simple change will suffice. One can see that simple changes won't do, just because The Heisenberg equations of motion with this theory are also satisfactory, and they're just what you want. I feel that the new change must be just about as drastic as the passage from the Bohr order theory to the quantum mechanics. I will stop there. I think it would probably be worse. In any case, I feel that the electromagnetic field and the electrons are the things that we know most about. And so I think it's preferable to concentrate one's attention, first of all, on the things that we know most about. A good many people think that that's perhaps a mistaken view, and that we shall never be able to solve these simple problems without solving all the problems of physics together. And I think that that's very ambitious if you hope to solve all the problems together. And I think that the most profitable line of progress is to separate the difficulties and dispose of them one by one. And if you cannot dispose of this difficulty of the interaction of the electrons and the electromagnetic field, you have very little hope of doing anything with the other fields. The gravitational field, which people are now considering to introduce, just brings in a lot more difficulties and doesn't help.
Would you think that having an infinite number of electrons in the nucleus imaging beam, like your subatomic, do you think that having those two in considering any more difficult physically?
Well, these negative energy states do help to that extent that I mentioned here, that this kind of infinity is reduced to this one. They do help, but not enough to solve the problem.
The idea of having an infinite number of electrons around, isn't that just as difficult?
The infinite density of electrons doesn't disturb things because it doesn't affect the equations of motion.
If you take a finite limit of that into thought, then do subtraction, and then if the limit goes infinity. I don't know enough about it, but is that helpful?
I did say that one should take this upper limit to correspond to somewhere around 1,000 millivolts. Why does one have to restrict it in that way? Well, this whole method of getting a solution of the wave equation following the standard perturbation theory is a valid method only if the later terms in the expansion are small compared with the earlier terms. And in order to secure that these later terms shall be small, it is necessary to have this limit sufficiently low. If we go on making this limit higher and higher, we get to a point where the later terms in the expansion will completely swamp the earlier terms, and then it doesn't seem to have much sense to discuss the earlier terms under those conditions. But the figure of 1,000 million volts is adequate to make the later terms small compared with the earlier terms, not very much smaller, but still somewhat smaller, and still adequate to give the Lang shift and the anomalous magnetic moment in reasonable agreement with observation. Thank you.